Let me start with a simple question. If you create a polymer in the lab, how do you really know what you made? Not just the chemical structure, but the size of the molecules. Are they all uniform, or is it a mixture of long and short chains? That's where gel permeation chromatography, or GPC, becomes essential. Today, I'll walk you through what GPC is, why it matters, and how it helps us truly understand polymer materials. Polymers are not made of identical molecules. When we synthesize a polymer, we don't get one perfect molecular weight. Instead, we get a distribution, a mixture of short and long chains. This molecular distribution directly controls material properties. For example, stronger plastics often have higher molecular weight. Flow behavior during processing depends on chain length. Mechanical durability depends on how uniform those chains are. That's why we measure key metrics like Mn, number average molecular weight, Mw, weight average molecular weight, PDI, the dispersity index. These values ensure consistency from batch to batch and help maintain product quality. So what exactly is GPC? GPC stands for Gel Permeation Chromatography, and it belongs to a broader technique called size exclusion chromatography. Unlike many chromatographic methods, GPC does not separate molecules based on chemical interaction. There's no polarity-based separation, no charge-based separation. It separates purely based on physical size, specifically hydrodynamic volume in solution. That means molecules are separated according to how big they behave in a solvent. And importantly, this is a non-destructive analysis. Your sample remains chemically unchanged. Now let's visualize how this works. Inside the GPC column are millions of porous beads. Think of them like microscopic sponges filled with winding tunnels. When a polymer solution enters the column, molecules travel through these beads. Large molecules are too big to enter the pores, so they take the fast path around the beads, and they elute first. Small molecules enter almost every pore. They take a long, winding journey, so they elute last. It's like a molecular obstacle course. And interestingly, the biggest molecules come out first. That's the core principle of size exclusion. Now, let's look at the actual instrument setup. A GPC system has 4 main components. First, the pump, which ensures constant solvent flow. Second, the injector, where we introduce our dissolved polymer sample. Third, the columns. These are packed with porous particles that perform the size separation. And finally, the detector, which collects the data as molecules exit the column. Each component must work precisely together for accurate molecular weight measurement. After analysis, the system produces a chromatogram. The chromatogram peak represents the molecular weight distribution of your polymer sample. From this curve, we calculate Mn, the arithmetic mean molecular weight, Mw, the mass-weighted molecular weight, PDI, which is Mw divided by Mn. If the PDI is close to 1, the polymer is highly uniform. If the PDI is larger, it indicates broader heterogeneity, meaning more variation in chain sizes. That single peak tells the entire story of your polymer distribution. Now let's move from theory to real laboratory practice. Success in GPC depends heavily on preparation and system stability. First, your polymer must be fully dissolved in the solvent. Incomplete dissolution leads to inaccurate results. Second, always filter your sample, typically using a 0.22 micrometer filter to prevent column clogging. Temperature control is also critical. Even small variations, plus or minus 0.1 degrees Celsius, can affect retention time. Calibration is equally important. Most systems use polystyrene standards, meaning results are relative unless you use absolute detectors like light scattering. And finally, regular maintenance is essential to protect expensive columns and maintain accuracy. GPC is widely used across industries. In manufacturing quality control, it ensures batch consistency in plastics like polyethylene and polypropylene. In pharmaceuticals, it characterizes drug delivery polymers and biopolymers. In research and development, it monitors reaction progress, degradation studies, and polymer modification. In short, GPC isn't just an analytical tool, it's a decision-making tool. Let's look at both strengths and constraints. The strengths. GPC directly measures molecular weight distribution. It's highly reproducible and widely standardized. And it's non-destructive. But there are limitations. Samples must be fully soluble. Results are calibration dependent unless absolute detectors are used. And the equipment and columns are expensive. Understanding both sides helps interpret data correctly. Let me leave you with one powerful statement. If you work with polymers and don't know your molecular weight distribution, you don't really know your material. That's the golden rule of polymer science. GPC acts as your molecular compass. It guides decisions about strength, processing behavior, performance, and reliability. And that's why it remains one of the most essential tools in polymer characterization.